Hey folks, today we're going to start a new unit. The unit is rotational kinematics and dynamics. And for this first couple videos, we're just going to focus on the kinematics. That's the motion of something going in a circle. Okay, so I'm going to make the analogy with the linear motion. So we've talked about linear motion, things moving up, down, left, right, in different shapes, parabolas, etc. Well, now we're going to talk about things spinning. Okay, so let's say we have our circle here, and let's say you are traveling in that circle, and let's say you're on the edge of the circle and you move from there to there. So from location 1 to location 2. All right. Well, you've gone a certain distance. We'll call that distance around that part of the circle, that's called S. Okay, and this just means a path. Okay, but you've also gone through an angular displacement, theta. Or you could say delta theta as well, but for now I'll just say theta. Okay. Now those two things are related to each other from math class, and I'll go one step further. Let's say you did one complete lap. Well, then you have traveled the circumference. And what does circumference equal? Well, it equals 2 pi times your radius. Well, what's 2 pi? Well, 2 pi is the angular displacement that you've done. If you've done one full lap, you've covered 2 pi radians. So when we do rotational kinematics, we are almost certainly, or almost always, will be converting our angular quantities to radians. Okay. Now you'll see degrees, you'll see revolutions, but you want to convert those to radians because in this equation, the angle has to be in radians for this relationship to work. Now, more generally, we say that the distance you go is equal to the angle, angular displacement, times the radius, and from now on, I'll just switch the order of this so it'll look like that, okay? But again, this equation only works if you're in radians, okay? So for instance, let's say you do half a lap. Well, then you've gone pi radians. How far have you actually moved along the circle's rim? You've done pi times r, meters, okay? So that's our first quantity we're going to talk about. We have an angular displacement, and usually it's in radians. Okay, now you might also see degrees. You might also see revolutions. Okay, and just remember, 2 pi radians is equal to 180 degrees is equal to 1 revolution. So, for instance, if you've got a problem which says the wheel is rotating at 60 RPM. That means revolutions per minute. You'd want to convert the revolutions to radians and the minutes to seconds, most likely, to use that number. Now, in a linear system, the analogy is you have a position. Okay, so you have an angular position and we have a linear position. Now, what if you're moving? Okay, what if you're spinning? Well, in a linear system, we have velocity, which is dx dt. In an angular system, we have omega. And it's not W, it's omega. And that is d theta dt. That's the derivative of theta. That's how quickly you're spinning. Also in a linear system, we have acceleration, which is dv dt. In an angular system, you have alpha, which is d omega dt. Okay, so that's the analogy. So these mean you're spinning. Okay, that's the rate at which you're spinning and the rate at which your spinning rate is changing. That's your alpha. Okay, now if just like over here, if a is constant, okay, then like for instance this equation here we can write as v final equals v naught plus at. Well, over here, if alpha is constant, we can write omega final equals omega naught plus alpha t. So the cool part is the equations are analogous if you just kind of learn the translation. So in a linear system, you have x, well, then you have theta in an angular system. In a linear system, you got v. Anywhere you see a v, you plug in an omega for an angular system, etc. So if you know the equation in a linear system, it's just a matter of subbing in the right things in the angular system. So for instance, if alpha is constant or if acceleration is constant, so we know an equation for in an angular or linear system, delta x equals v naught t plus 1/2 at squared. That's again if acceleration is constant. Well, if alpha is constant, we have delta theta equals omega naught t plus 1/2 alpha t squared. Okay, now by the way, another way to write both of these would be to say um, or theta as a function of time equals theta naught plus omega naught t plus 1/2 alpha t squared. That's the same equation. We're just flushing out the delta in there. It's the same thing in the linear system. Similarly, in a linear system, we have v final squared equals v naught squared plus 2a delta x. Now again, this is only true if acceleration is constant. Okay. In an angular system, we have the analogous equation. We have omega final squared equals omega naught squared plus 2 alpha delta theta. So now we're really into the Greek letters here. Okay, so it's the same equation. Now these come from, in a linear system, if acceleration is constant, v average equals the average of the starting and the final velocities. In an angular system, that would be omega average equals omega naught plus omega final over 2. Okay. Now again, those last several equations rely on either alpha or acceleration being constant. Okay. Now the equations that always work, and I'll put them in boxes, this equation always works no matter what. And this equation always works no matter what if you have things as functions of time. Okay. Two other equations that are always going to work in both systems. I know in a linear system, average velocity always equals delta x over t. That always works. And acceleration average equals delta, oh, sorry, I was jumping ahead there, equals delta v over t. This always works. Well, in an angular system, the analogous equations would also always work. Average omega is delta theta over t. That always works. And average alpha equals delta omega over t. That always works. Okay, so the things I put in boxes here, those always work. Okay, and in a linear system, these would always work too. Obviously, we've talked about that previously. Okay, other things that you should know. Okay, going back over to here, we know S equals R theta. Well, if I take the derivative of both sides, on the left side, as a function of time, if I take the derivative with respect to time, over here we get ds dt. R is going to be constant. You're not going to change the radius of your circle. And over here you get d theta dt. All right, what does that mean? Well, ds dt, that's velocity. It's the same thing as dx dt. So that's velocity equals r, and what's d theta dt? Well, that's omega. Okay. And if you do that process again, if you take the derivative again, you're going to get the derivative of velocity is acceleration, and the derivative of omega is alpha. Okay, so these three guys are our translators. This translates an angular quantity, whether it be theta, omega, or alpha, into its analogous linear quantity, which is s, that's path length, tangential velocity, and you probably should put a little t there, that's tangential velocity. And then we also have tangential acceleration. So what that means is for tangential velocity, if you were moving right there, let's say, and you're moving this way, what would your speedometer say? How many meters per second would it say? And then the tangential acceleration is simply how fast you're speeding up or slowing down as you travel in that circle. And then I've got one final one for you guys. If you're moving in a circle, we know that we also have radial acceleration. Okay, and you guys know that formula, AR is v squared over r. Okay, well, I also know that v equals r omega. That's this right here. Okay, so if I sub this in here, another way to write radial acceleration, if you square the r's and the omegas and then one r drops out, you get r omega squared. You can use either of these just depending on what you're given in the problem. Okay, they both have the same units and so on. Okay, So that's an overview of the equations that we're going to be using for rotational kinematics for the next several chapters. The next video, I will do several examples with you to kind of talk about these equations. But what you're going to notice about some of the examples is it's very much like doing linear motion. So if you understand linear kinematics, the rotational kinematics is the same idea. The only difference is instead of talking about how far we're going, okay, we're talking about how far we've rotated. Okay, so that's how many radians we've rotated through. So that's the big difference there. All right, so I hope that was helpful, and I'll see you in the next one.